All right, this video is going to be dedicated to finding the area of a polar region. Since polar regions are circular in nature, we're going to base the area of these regions off of circles. So let's just look at a circle. If we're going to find the area, we know the area of a circle is pi r squared, but if we're going to find the area of these polar regions, we're going to divide them up into sectors. So if you notice, I have a sector divided out here. We're going to find the area of one sector and then integrate that over a larger area. So I'm going to find the area of a sector of a circle, and we'll use that idea then to find the area of the polar region. Okay, so the sector of a circle would be some part of a circle that spans some angle measure. And if we know the radius r, we know the area of this whole circle is pi r squared, and the area of the sector is some fraction of that. So the fraction, to determine what fraction it is, we're going to take that angle theta, and it's some fraction of 2 pi, because 2 pi is all the way around. So if we multiply that fraction times the area of the entire circle, that's the area of a sector. Now we can simplify a little bit. Those pi's will end up canceling each other out. So the way you normally see the area of a sector is 1/2, because pi over 2 pi is 1/2, times the radius squared, times the radius squared, times the angle measure. Okay, so in our case, we've got this angle measure here, and we know the radius of the polar graph, and it changes based on the function that we're using to graph the polar region. Now, if we're going to put an infinite number of these things inside of this polar region, that theta value is going to get smaller and smaller. So theta becomes d theta. So what we're going to say then is the area of a polar region on the interval from one angle to another, because we're rotating about a circular region. So from alpha to beta is given by this. From alpha to beta, 1/2 the radius squared, and since theta is getting smaller and smaller, we'll call that d theta. Okay, so this is the premise, this is the basis that we're going to use for the area of any polar region. It's the antiderivative of 1/2 r squared. In order to do this and to integrate by hand, we're going to have to use, or get to use, growth mindset, we're going to get to use a trig identity, or 2 trig identities that are going to come in handy. So these 2 trig identities are ones that you don't use a lot, but they're going to come in handy here. Sine squared theta is the same as 1 minus cosine of 2 theta over 2, and I'm going to simplify that for when we actually start to integrate. I'm going to write this as 1/2 minus 1/2 cosine of 2 theta. And the reason we change sine squared into cosine of 2 theta is because sine squared is, we can't integrate that. That's not u substitution. However, we can integrate the cosine of 2 theta because that's just a simple u substitution with 2 theta. So I will simplify this one as well to 1/2 plus 1/2 cosine 2 theta. You're going to have to know those. Okay, let's go on. We've got all of the things we're going to need. Let's put this into action. So here's the first example. Find the area of the interior of r equals 3 cosine theta. So I'm going to graph out this region. I'll do this first one all the way through, and then you can try the next one on your own. So 3 cosine theta, I'm just going to graph this on a rectangular coordinate first, because for me that's easier. I like to visualize it. So I know that cosine is 0 there. 3 there, 0 there. At pi, we're down to -3 now. At 3 pi over 2, we're back to 0. And at 2 pi, we've completed one cycle. And those are important things to note with these graphs. We need to know how long a cycle is, because we may have to repeat it in order to get everything that we need. And we need to know where this graph crosses the x-axis. I want you to note how great that cosine graph was, by the way. The first one was not so great, but I made up for it. All right, let's graph this on a polar set of axes. So we need to have 3 circles since the amplitude is 3. I'm not going to worry about making them perfect because I don't want to take up too much of your time. So that's 3. Just pretend they're equidistant from each other. All right, if I start graphing this, I know that at 0, the value is 3. The R value is 3 because that's what I found. At pi over 2, the graph has a value of 0, so we're back here at the pole. So if I start graphing this out, this is the direction we're going. Okay, when I get to pi, the value is actually -3. So what that does is it puts us back over to 0 again. It puts us back here. Okay, let's keep going to make sure there's not more to this graph. If I'm back at 3 pi over 2, I'm back at 0 again. Okay, so this thing is just going to continue to spin around the graph and look like this. So really the only regions we're looking at is from here to here. That region is what graphed out the interior of r equals 3 cosine theta. So what we're going to do is I'm going to find the area 2 different ways. I'm going to just show you that there are 2 different ways you can do this, because eventually shortening it is it's not really shortening it, but changing it in a different way is going to come in handy. So trust me on this one. We could say that the area is from 0 to pi, and that would be 1/2 times the radius squared. Or, because the area on the top of this is the same as the area below, so this is symmetric, I could say, well, there are 2 of the same area from 0 to pi over 2. And again, we're going to get the same area. I'm going to solve these both out, but I just want you to know that there are 2 ways to do this because it's going to come in handy. All right, so I'm going to solve the one on the right. I know that 3 squared is 9, and 9 times 1/2 is a constant, so I'm going to pull that constant out. And then cosine squared theta. So now this is where that identity is going to come in handy, because I can't find the antiderivative of cosine squared. I cannot just use u substitution, so I'm going to write this as 1/2 plus 1/2 cosine of 2 theta. Now I can integrate each one of those separately. The antiderivative of 1/2 with respect to theta is 1/2 theta. Using u substitution on the second one, u is 2 theta, du is 1/2 d theta. Oops, sorry, it's 2, I was thinking too far ahead, is 2 d theta. So if I multiply by 1/2, 1/2 du is d theta. So this becomes 1/4 then, because I already have a half times another half is 1/4 cosine of 2 theta. It's the antiderivative. And I'm going to evaluate that from 0 to pi. All right, so if I plug in pi, I get 1/2 pi. Oh, the antiderivative of cosine is sine. Wow. You knew that, right? The antiderivative of cosine is sine. So now if I plug pi in for theta, that's 2 pi. The sine of 2 pi is just 0. Okay, now if I plug in 0 for theta, that's 0. The sine 2 theta, so 2 times 0 is 0. Sine of 0 is also 0. So that's all 0. This becomes 9/4 pi. That's the area of that region. I'm going to do it the other way, where I'm only going to find half and then just double it. Because I just want to show you, I mean, I know intuitively it makes sense. I just want to show you that it really is going to turn out to be the same. So first of all, this 2 here and this 1/2 become 1. And 3 squared is 9, so I'll pull that constant 9 out. And this is cosine squared 2 theta. Cosine squared theta. If I use that identity, this becomes 1/2 plus 1/2 cosine 2 theta. See, that's where my mind was going. If I find the antiderivative, which we already did up in the previous one, let's make sure it's sine this time. If I evaluate that at pi over 2, I get 1/2 times pi over 2 plus 1/4 times the sine, so 2 theta. 2 times pi over 2 is pi. Sine of pi is 0. Minus, if I plug in 0, that's 0 and 0. So I get 1/4 pi times 9 is 9 pi over 4, or 9/4 pi. So either way we did it, we got the same answer, and sometimes it's going to be easier to find just half and double it versus finding the entire thing. Okay, sorry for a couple of those flubs. Let's see if I can get smoother. Let's move on to the next one. Find the area of one petal on the polar graph defined by 4 sine 3 theta. I'm going to give you an opportunity to try graphing this. So please pause it, graph this rectangularly if you want, and then polarly as well. Okay, welcome back. I'm going to graph this in the rectangular form first. First of all, I see the amplitude is 4. And I see that this is not, normally sine has a range of 2 pi, but because this is moving 3 times as fast, it will be done with one cycle, one period, at 2 pi over 3. Halfway, pi over 3, half of that, pi over 6, halfway here, pi over 2. All right, this is sine of 3 theta, so I know that sine starts at 0. At pi over 6, we're up at 4. Pi over 3, we're back to 0. Pi over 2, we're down to -4, and then we're back to 0 again. Those are the important things. We need at least one cycle, perhaps 2, maybe 1.5. You just have to draw it out until we see if we get it all. And we also need to know where it crosses the x-axis, the roots or the solutions. Okay, so let's graph this out. Let's see if we can get kind of an idea. We're looking for one petal on this graph. Okay, so I'm going to draw 4 concentric circles. I'm not going to worry about how equal they are. I'm going to plot as many points as I need to get one petal. Okay, so at 0, we're at 0. So that's here at the middle in the pole. Pi over 6 is about here. Pi over 6 is about 30 degrees. And the radius is 4 there. And then at pi over 3, we're back to 0 again. Pi over 3 is about here, but we're back to 0 again. Okay, this is the orientation. That looks like it's probably one petal, but let's keep going. All right, at pi over 2, the value is -4, so pi over 2 is up here, but -4 will graph that point down below. And then 2 pi over 3 is back to 0 again. So I can see that this is indeed one petal. I've graphed 2. There are more than just 2 on this graph, but one petal is all it asks for, so I'm going to stop right here. That petal shows up here, but I can also see that that petal is symmetric. So instead of finding the whole thing, I'm just going to find the area of one side and then double it. And that shows up here. This is the region, that's the one side. That's what we're going to find, is from 0 to pi over 6. All right, so I'm going to say there are 2 of these regions. And we're going to go from 0 to pi over 6 would be enough. 1/2 r squared d theta. The 1/2 and the 2 become 1. The 4 squared is 16. Okay, I'm going to have to use, or I get to use, that identity. So remember that sine squared theta is equal to 1/2 minus 1/2 cosine of 2 theta. Well, in this case, our theta is this. So we're replacing theta with 3 theta. So the sine squared of 3 theta is 1/2 minus 1/2 the cosine of 2 times 3 theta. So it'll be 1/2 minus 1/2 the cosine of 6 theta. Okay, I'm going to make that replacement over here. I'm going to use that substitution. It's 1/2 minus 1/2 cosine of 6 theta. So now when we use u substitution, u is going to be 6 theta. du is 6, And we need to do 1/6 du is d theta. So I'm going to multiply that by 1/6. All right, let's integrate this. Antiderivative of 1/2 is 1/2 theta. 1/2 times 1/6 is 1/12. Antiderivative of cosine is sine. Look at me getting this now. And we're integrating from 0 to pi over 6. All right, let's plug this in. I'm going to plug pi over 6 in for theta. I'm going to replace theta with pi over 6 here. Pi over 6 times 6 is pi. The sine of pi is 0. Minus, if I plug 0 in, that's 0. Sine of 0 is 0. Simplifying this then, I get pi over 12 times 16 is 16 pi over 12. If I reduce that, the area is 4 pi over 3 units squared. Okay, let's do one more. Find the area of the common interior for these two graphs. So this one's going to get a little bit complicated. There's going to be a lot of graphing going on, but I want you to give it a try. So go graph these two. Welcome back. I hope you actually did it. I'm going to distribute the 2 into both of these to make this a little bit easier. All right, I'm going to graph each of them. First of all, I can see that they're both shifted up 2. So I'm going to adjust my graph here just a little bit. I'm going to think about this, because we're shifted up 2, I'm going to think about this as my new x-axis. This is just a regular cosine theta. It's not the cosine of 2 theta or anything like that. So I know that the period is 2 pi, halfway is pi, half is pi over 2, halfway is 3 pi over 2. All right, I'm going to graph these points and see if that's going to give me some x-intercepts or some, at least intersection points of these two graphs. That's the important part. All right, so let's graph this first one. First of all, I know that cosine normally starts at 1, but because we're changing the amplitude, this one's going to start 2 units above our new x-axis. So we're going to start up here. And then from there, cosine is 0, and then negative, and then back to 0, and then up here. So here's my first one. I'm going to use a different color for the other one so it's a little more obvious. Yeah, it wasn't as good as my last one, but it's not bad. All right, now I'm going to graph the other one. This is the same cosine graph, but negative instead. So instead of starting up at 2, we're going to start at 0, here, 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 and here. The nice part about this is that we found the intersection points of these two graphs without having to do any extra work. Pretend they intersect there, and then they definitely intersect there. That's going to come in handy. So if I graph this out now, I'm going to use purple. I'm kind of tired of orange. I can see that my largest value is 4, so I'm going to need 4 concentric circles. I'm going to make that just a little better because my drawing is going to be a little more important this time. All right, I'm going to draw the orange one first, so I can see that at 0, I have a value of 4. So graph that there. At pi over 2, I have a value of 2. So from here to here. At pi, I have a value of 0. At 3 pi over 2, I have a value of 2. At 2 pi, I have a value of 4. It's a heart. We call that a cardioid. So that graphed out a heart. I'm going to use red for the other one because purple I think will be hard to see on that. So I'm going to graph the purple one in red. At 0, we have a value of 0. Pi over 2 is 2. At pi, we have a value of positive 4. At 3 pi over 2, we have a value of 2. And at 2 pi, we're back to 0 again. Also a cardioid, but backwards. That was what that negative did. The question says, find the area of the common interior. Well, the common interior, this is kind of getting messy because I used a dark color. The common interior is all of this. So this is where what I was saying before is really going to come in handy. What I see is that we actually have 4 of the same areas put together because this is all symmetric. I have 4 of these areas all put together. 1, 2, 3, and 4. So I'm only going to find the area of one of those and then go from there. So what I noticed is on the red one, on the red curve, so this purple one right here, we went from 0 to 2 between 0 and pi over 2. So in other words, we started graphing here and then we went here. So if I just find the area between 0 and pi over 2 for that graph, I can just multiply that by 4 and I'm done. I hope you can see that. If not, we'll talk more in class. So what I'm going to say then is I only need this purple curve. I only need this one. And I'm only going to find the area of that from 0 to pi over 2, and I'll just multiply that times 4. Because there are 4 of the same region. Okay, so this is from 0 to pi over 2. 1/2, and r in this case was 2 minus 2 cosine theta squared. Okay, let's do some multiplying. We'll solve this out. I'd like you to just stop this honestly and go try it yourself. I'm going to multiply the 1/2 and the 4 and make this 2 outside. I hope you go try this yourself because I think this is something you could easily do without my help. So I just distributed those, and now I'm going to change my cosine squared into the identity that's useful. And if I distribute that 4, this is really going to be nice to integrate. The nice part about this to integrate is I already have the u prime right there. I don't have to multiply by anything weird. So the antiderivative of that will just be sine of 2 theta. All right, so I'm going to integrate. The 4 and the 2 are 6, so this becomes 6 theta minus 8 sine theta plus sine 2 theta. And I'll integrate that from 0 to pi over 2. All right, to do that then, 6 times pi over 2 is 3 pi. The sine of pi over 2 is 1, so this becomes 8. Pi over 2 times 2 is just pi, so the sine of pi becomes 0. All right, now if I plug 0 in, 6 times theta, that's 0. The sine of 0 is 0, and the sine of 0 is 0. Okay. So this becomes 18 pi minus, or 6 pi minus 16. That's the area of that region, of the common interior that they shared. Okay, that's it. This was a long one, sorry.